So good morning, I am Krishna Kumar, again from Krishna's classroom. We continue from where we left last time. Last time we introduced the lines in R2 and then their complementary spaces. And then of course we looked at what exactly is the complementary space or the complementary spaces look like. From that we constructed a set of lines parallel to the given line, which is the one-dimensional subspace that we were considering in that space. Then we found that there is a meaningful way in which you can add these lines to get other parallel lines, and you can also talk about what is called scalar multiplication, and essentially the lines parallel to a given line forming a vector space. Now what is this vector space all about? This is what we want to look at. Maybe it's more interesting to look at R3, where you have more varieties. Like you have non-trivial subspaces which are of dimension 2 and 1. The vector spaces or the subspaces of dimension 2 are all planes passing through the origin, and the subspaces of dimension 1 are all lines passing through the origin. So in both these cases we will try to explore whether parallel lines and parallel planes would have the structure of linear spaces. That is what we are after. So we start with the example R3. F we take as R. So dimension of R3 is 3. Subspaces are non-trivial R. Lines through the origin. And this is one dimension. And then you have what are called planes. What are two-dimensional surfaces or two-dimensional subspaces? These are the only one-dimensional and two-dimensional subspaces which are non-trivial. And you have got the trivial subspaces, namely the one consisting of the zero element alone, which is zero-dimensional, and the three-dimensional subspace, that is the whole space. So let us see what you can make out of these two types of non-trivial subspaces. So we start with lines through the origin. So what you do, what you have is, you have the three-dimensional space, This is the 1 axis, this is the 2 axis, and this is the 3 axis. And the standard coordinate system. Now what one has is a straight line passing through the typical one, and which is as usual generated by a non-zero vector v. This vector can be in this direction also, doesn't matter. And then you see that an arbitrary point on this is going to be P. Now U has components U1, U2, U3 with respect to the coordinate system. So when U can be written as U1, U2, that is the coordinate system with respect to the standard coordinates system that we have introduced. Now you see that the line, an arbitrary point on this line is of the form PU, therefore the equation of the line is line generated by U is x equal to T, where T belongs to. Or let me write is a set LU defined as a set of all x in R3 this collection. So these are the points that you have. This line is denoted by LU. Okay. Now what we can do is, as you did in R2, you can take a vector A not in this line, this is LU. When you take LUA, translate the set of all x belonging to R3 this is the parametric form with the see we have taken A not equal to A does not belong to LU. This is fixed. Then you can translate through the vector A. So what you end up will be another line in R3. A line in R3 which passes through the tip of the vector A and parallel to the given line LU. So this is your LU A. Now suppose A is equal to A1 with respect to the standard coordinate system that we have introduced, and A does not belong to LU. So what one gets is the parallel translate of this line, as these two lines are parallel. Now let us look at the scalar form of it, which you have or analytical form of it. Analytical form of LU. This is actually x1 equal to x2 equal to this is the parametric form, or conventionally we write x1 by u1 equal to this is it's a formal way of writing which only tells that the vector x1 x2 is along the vector u1 u2, or what you call the direction ratios of LU are there is also sometimes the representation will come when u is not equal to 0, still one of the components or two of the components can be 0. In that case, we will be writing x1 by 0 equal to x2 equal to 0 equal to x3 by u2, something like that. But that is not simply division. Okay? The meaning of this is this, in fact. This is the scalar form, and if you eliminate t between them, this is what you end up with. And this is the conventional form in which you have seen a line whose direction ratios are given by u1, u2, u3 and passes through the point 0, 0, 0. What about LU? This is, of course, you see that x is equal to tu minus plus a, or x minus, the vector form is x minus a, or you can write this as and x3 equal to a3 plus or in the standard form in which you often write it as x minus a1 by or the line that you have LUA is parallel to the line LU. Both have the same direction ratios. The difference is that the LU passes through the point 0, 0, 0, but this does not pass through it. In fact, by choosing different A, one can get all lines parallel to this. Now you see, you are in R3. When you are in R3, see, you have a line and you have got lines all around. Okay, it's not lying in a plane alone. There are lines all around. So it's almost like a, this broom that you would have seen, with a lot of sticks tied around. And then they're all, we can take them as parallel lines. So something like that. So you have got several situations. If you want to give a three-dimensional view, I will just take another line here, generated by a vector B. So this is L U B, and LUB may be such that LUB, LU and LUA need not lie in the same plane. Okay, so you can choose a B such that LUB is and LUA do not share the same plane with LU, or the plane containing LUA and LUB does not contain LU. Such lines can be obtained. So in fact you have one line and all around there is lines. So there is a lot more space now since you are in R. So that's something to be understood, and this is the equation of the line. Once again, all the comments I made about U1, U2, U3 coming in the denominator is valid. So that's fine. Okay. Now what you have, now we can once again classify all vectors as we did in the case of R2 into different classes. Okay. For instance, you have seen that if you have A here, if you take any other vector on this line, say A prime, suppose A prime belongs to then you have L, another line that you can generate, LUA prime. What is the relation between LUA and LUA prime? Okay. You can easily see that if A prime belongs to LUA, A prime is equal to some T1 U plus A. Okay, A1 belongs to A prime, therefore you see that A minus A prime equal to T1 okay. This is the relation between A and A prime. So this has three relations, namely A1 minus, so that is A1 minus A1 prime equal to T1 U1, A1 A2 minus A2 prime equal to T1 U2, A3 minus A3 prime equal to T1, this relationship. Now let us look at this one. Okay, so you have, see, let us take LUA prime. LUA prime is essentially x1 minus A1 prime divided by U1, x2 minus A2 prime divided by U2, x3 minus A3 prime divided by U2. And substitute from here for A1 prime, A2 prime and A3 prime. Okay. then what do you get? This is equal to, that is x1 minus a1 prime, I can replace by a1 minus e1 u1. Okay, then similar statements are there. Okay. So, now this gives, suppose you write this as some s, then what do you have? You have equal to s u1 minus u2. Similarly, x2 minus a2 equal to t1 u2 or s, and x3 minus a3 equal to s therefore you end up with a relation something like this: x1 minus a1 by u1 equal to so you see that x1, x2, x3 also satisfies this equation. Okay, therefore these two lines are one and the same. At every point, in fact, more rigorously one can prove that LUA if A minus A prime now this is the sort of result that we proved in the last lecture. Okay. Fine. Therefore, now you see that all these are, in fact, once you fix this line, now all these lines are for the choice of A, define A, to get parallel lines. Okay. So here what you have done is that if A and A prime belong to LU, sorry, A and A prime are points in R3 such that A minus A prime belongs to LU, then LUA is the same as LUA prime. Therefore, LUA is generated not only by one point but several points. Okay, all points A prime with the property that A minus A prime belongs to LU. That is the condition. So this happens with all parallel lines. Okay, as we have seen in this case. Now therefore, let us work this out. We can say that A is related to A prime okay, A is related to A prime if A minus A prime belongs to A. Now we show that this is an equivalence relation on the class of all vectors in R. So this relation is an equivalence that is very simple to verify. So I leave it to you. Three things are to be verified. A is related to A. A minus A is 0, which is 0. A is related to A prime, implies A prime is related to A. Obvious. A1, A is related to A prime, and A prime is related to A tilde, then A is related to A. So all the three things, namely the reflexivity, symmetry and transitivity are satisfied. Therefore, it is an equivalence relation. It induces, or the given line LU induces an equivalence relation on all vectors in R3, and therefore it partitions the vectors into disjoint classes. Okay, so that's what we have as we did before. Therefore, now you see you are in a position to talk about the sum of lines. Okay. What is sum of line? So you say that see LUA plus LB defined as the meaning is obvious. Okay, what is it? LUA plus LUB equal to LUA plus B. The situation is exactly like we did last time. Geometry is the following. You have got R3. You have a line LU, this is LU. You have another line. Okay, this is A. Then you have another vector B. Give you a line. Now what do you do? We can add these two vectors using parallelogram law and then get another So this is A, B. Now this is diagonal. You complete the parallelogram, and this is the vector. Okay. Then you have a line passing through the tip of this parallel to L. So the sum of these two vectors is, see, this is one vector, sorry, this is one line, this is another line, and this one corresponds to A, this one corresponds to A, and sorry, this one corresponds to B, and this one corresponds to yellow one. Now when you add this yellow line to the orange line, you end up with the line, the green, the blue one, parallel to both, and also parallel to the original line that you have. Because what you do is you take the parallelogram law of addition, and then to the tip of this there is a unique line, and you claim that this is true. We have to substantiate it. First of all, the difficulty comes from the following. It is not only A which can generate LUA, but A prime which is lying on this line can also generate the same thing. Okay. So what you have is, there is another point A prime here. Then there could be another point, see, B prime here. So this is B prime. Now what you want is, you want to really add them. Add these two. Complete the parallelogram and add them. Do you end up with this? This is the question that you are asking. Do you end up with a point on the same, on the line L, U, A plus B? Okay. This is A prime plus B prime. Okay? Let us prove this. In fact, you have to prove it. Not every time, for every pair, all this. So you know that, suppose A prime and B prime also lie on LUA and then what you have, this is happens if and only A minus A prime belongs to LU, B minus B prime okay. So now you see, you have X. So you take, your claim is this, L of U A plus B when does this happen? This happens with, if A plus B is, and now this happens if and only if This is the claim. This if and only if you have a plus b minus a prime plus b prime, which is equal to a minus a prime plus b minus b prime. This is in LU, this is also in LU, and LU is a subspace, therefore this belongs to LU. Therefore you see that if A prime and B prime are points on LUA and LUB respectively, then you have LUA plus B equal to LUA prime plus B prime. Okay? Therefore, once this equivalence relation is, you see, once this relation is an equivalence relation, you see that some of these vectors do generate the same line. That's what you have. Some of them generate totally different lines. In fact, you see that with this relation, what we are doing is we are classifying the entire class of vectors in R3. Okay? Into classes which generate the same line. Right? And we have seen that being an equivalence relation, it partitions the whole space or R3 into different classes, that is into boxes of vectors, disjoint boxes of vectors. Every vector in R3 is in one of the box, and all the vectors in the same box have the property that they generate the same line. Okay? So that's what you have. So what we have proved is that if A and A prime generate the same line, B and B prime generate the same line, then the line generated by A plus B is the same as the line generated by A prime plus B prime. Therefore, the addition that we have defined here is well defined. There is no ambiguity, irrespective of what representation you use to work on this. Now, so also you can actually prove this. If you have, say, you take R3 again, you have a line passing through the origin. Take a vector A, then you have a line. You have a line here parallel to it. So this is LU, this is LUA. Now you take L lambda A. Lambda A is the scaling of this. Suppose this is the point lambda for some lambda. I mean, lambda may not be always positive, it can be going the other way around also. Then you see it generates a line. So you have L U lambda, this is the line. Okay? Now you see, you start taking another A prime. So A prime, see, you have L U A. Then what you claim is this: L U lambda A is the same as A prime. All that you need to show is that, see, already you have A minus A prime belongs to LU. You have to check, does this imply This is so because lambda times A minus A prime. This is in LU. Lambda is a scalar. LU is a subspace. Therefore, this belongs to. So that is verified. Okay, so you get your scalar multiplication, and the consequence is that whether you work with A or A prime, as long as they are related to this relation, then you see that the two lines generated by it, the line generated by A and A prime are the same, which in turn implies the lines generated by lambda A and lambda A prime are the same. Or scalar multiplication, irrespective of what representation you use, you always end up with the same line. Okay? Or in other words, this implies LU lambda A can be defined as so what do you need? Take any vector here, it can be written as lambda times a vector here. Okay? So that's what you have. And it is like irrespective of what vector you choose, this is always true. So the scalar multiplication is also well defined. So now you have addition, scalar multiplication, and then you ask whether it is a linear space structure. And I think I need you to work out that. So this addition and scalar multiplication endorse the lines of the space of all lines parallel to the given line vector space that's important. So given LU, take all lines parallelly, you can meaningfully define an addition and a scalar multiplication, and the consequence is that with respect to this addition and scalar multiplication, it becomes a vector space. Here the zero element of this new vector space is the line LU. Okay? Note the zero element or the identity element. The line that passes through that. So we can leave it at that. Now we take up the case of two-dimensional structure. So now there are deeper questions that come around that we will resolve in a general scenario. Namely, what is the dimension of this space? Naturally, if you have a linear space, can we find a basis for it? What is the dimension of the space? And these are the key questions that we immediately ask you. and there is some kind of isomorphism that you can establish with some spaces and so on. So these are the usual questions that you can ask here. But now let us take two-dimensional what you have in R3, you know that all the two-dimensional subspaces have been characterized as planes passing through the origin. So what you do is you take two linearly independent vectors, say U and V, and then construct a plane containing them. So this is what we call L, P. So we choose two linearly independent. Consider this plane containing these vectors. That is, what is that? So this is E, we call this E U V, essentially the set of what E V plus S V E U V S. For a typical element of this is x equal to the EU this is the plane. This is EU. Now what happens? Suppose you take a vector A. You choose a vector A which does not belong to the plane span by or the linear span of then translate so what you get? A typical element is x is equal to it's a parameter. What this stands for is a plane parallel to this is P. Z semicolon U. the fact that it is parallel follows from the fact that we add vectors using parallelogram law. That's the reason. Take a typical vector here, transport it, to see that they lie on the same plane. Okay? Or in other words, if you were to write this in the form of this, so what you have is the original plane PUD can be written as, is written in the parametric form is correct. So you have three equations, namely x1 equal to du1 plus sv1, x2 equal to du2 plus sv2, x3 equal to t. Now eliminate the two parameters t and v between these three equations. That means take the first two equations and solve for t and s, and then substitute in the third, or wherever you can do this. I mean, it depends on the values of u1, v1, u2, v2 and so on. Okay. So in short, what we have is this, that is u1, u2, u3, v1, v2, v3, they are linearly independent. Therefore, the eliminant of this would give you an equation of the type x1 equal to x2 u. This is what you get, which is of the form, say something like a1 equal to 0, or constants a1, a2, a3 which are determined by u1, v1, u2, v2, u3, v3. Okay, and this is typically a equation of a line of, a plane passing through the origin. Okay, now what you get, PUVA is then given by u3 plus s v3 a3, or these are the set of points. Now this again gives you two equations, namely x1 minus and the eliminant of T and S between them would give you the equation x1 minus a1, x2 minus a2, x3 minus a3 by this determinant, that is u1, v1, u2, v2, u3, v3 equal to 0, which you immediately verify that this is on the form a1 x1 plus a2 some constants. And you know that from your classical analytical geometry, you know that this gives you a line parallel to the, a plane parallel to the original plane that you started. So PUV and PUV this is what you mean by the parallel transformation. Okay. Having got this, once again you ask the following question. See, you can immediately see that if you were to choose A and A prime in the same plane, they generate the same plane. So you can show that. A prime belonging to or equivalently, that is A minus A prime belonging to B. The vector A minus A prime belonging to B. So here I mean the point A prime, the tip of the vector. So you know what distribution. Right. So this is what you have. Okay. And then again we can introduce a relation A prime. This is the definition. This is an equivalence relation. And once again, it classifies vectors into disjoint classes whose union is the whole of R. Okay. Therefore, you see that now we have a given plane and all planes parallel to it. When the analogy is, you would have seen the idli making vessel in which you have the various decks which one put on top of the other and held by a central sort of axis sort of thing. Okay, so one is apparently something like the translated. Or you take any book, you see, you look at all these sheets that you have, the pages, they are all parallel planes. Okay, no common point between them. mean, I am not talking about the hinge here, but otherwise, you see, these planes. This is the picture image, the picture that emerges. Okay. Now, can you, as before, work on the addition of vectors? One can easily check that this is possible without ambiguity. That means you define P A U B A plus P U B B defined by P this is the resolution. And you can show that this addition is again unambiguous. That means if you were to use an A prime and B prime, then as such this formula gives you A prime plus B prime. Then in that case, you see that P U B A plus B is the same as P U B A prime plus B. So this addition is very fine. So also you can define a scalar multiplication, and the scalar multiplication can be defined by P U lambda A. You can define as whether you work with A or work with A prime. Once A and A prime are equivalent, you see you end up with the same, lambda A will be the same plane. You end up with the same plane. And that is very easy to show. So you see that addition and scalar multiplication can be defined. So these parallel planes, parallel to the given plane through the origin, which are the cosets that you obtain through translation, are form a vector space that you have to show. I mean, the zero element here is the plane that passes through the origin parallel to every one of these. Okay, and then of course you can show that all the requirements of addition and scalar multiplication required for the collection to be a vector space are satisfied. So you see that the space of parallel planes to a given plane can be endowed with a linear space structure, or it inherits a linear space structure. Okay, so we have seen that through this process, two types of linear spaces we have constructed in R3. One, parallel lines to a given line through the origin, then parallel planes to a plane through the origin. In both these cases, you could do the same exercise and endows the collection of objects with a vector space structure. Okay, right? Now these translated lines and planes are generally called cosets. Okay, and the vector spaces that we have created are called the quotient space. Okay, so this is how the quotient spaces are constructed. Now you see that we will make some guesses. Right. In 2 dimension, we have the parallel lines and they form a vector space. Okay. So let me draw some pictures. So this will give you a indication. make some observations. Now you see that you take R, 2 dimensions, in which a line through the origin is given. This is what we call L. Now through A you can translate. Now what you have is, you have several lines parallel. In fact, the whole space or R2 is now stratified into parallel lines, or the union of all these parallel lines form. So what you have is L U A union of this, or A belonging to R. This is result. Okay, and you also have LUA empty whenever A is not equivalent to. So whenever A is equivalent to B, they are identical, and whenever A is not equivalent to B, so I have cut here, watch this. This is not equivalent to B in the sense that A minus B belongs to LU. Then you see that these are disjoint lines. So you get a collection of disjoint lines. We have defined addition, we have defined scalar multiplication, and then we have made a vector space. Now you see that, suppose you take this A and draw this. This is your A, and you have taken scalar multiplication. So let me use another color to code it. So this is your A, and this is the line. Now you see that this line cuts every one of these lines. Okay, because A is not in LU. Since A is not in LU, that this line generated by A cuts every one of this exactly at one point. Okay, and you see that they are generated by this. So some point that you have is something like lambda. Okay, so you see that just with one vector here, you can generate the whole class of parallel lines. Okay, with one non-zero vector which does not lie in LU, you can generate the entire class of lines parallel to it, or the entire class of the quotient space, or the set of quotients that we were talking about. So what you infer? You infer the following, that this is a one-dimensional vector space. Okay, so the set of all quotients with the endowed structure is a one-dimensional vector space. Okay, right? So from R2 we have this perception. Now see, there is another point. You can, as I said, there is another B may generate the same vector, and B also may generate a line which cuts every one of these lines exactly at one point. Okay, so you see that this also could be a generator. B also could be a generator Okay, so you have a B. B is generating a line. Okay. So B also generates the same parallel lines provided A minus B is N. Okay. In short, see, L U A, this singleton line and this singleton line L U B could be generating the same vector space or generating the same vector space. So one dimensional vector space, as I said. Okay. At the same time, you see that if you see the scenario in R2, you see that these two lines are not linearly dependent. They are not one and the same. Okay. In fact, you see that once this line is given, original line is fixed, there are infinitely many lines in R2 which can, along with the line LU, generate the whole of R2. Not just one line, but infinitely many lines. Now this is the important point. Okay? So everyone generates the same parallel lines. Okay? Because of this identification, that's LUA can be identified with LUB provided A and B are related. Okay? So in fact, there are several ways in which you can choose the basis for the quotient, but you end up with a several ways in which you can choose the basis for R2 to join the basic one-dimensional space that you have fixed. Okay. However, in the quotient class or the vector space of these quotients, you have a unique choice of a basis. Okay. I mean, unique choice in the sense a scalar multiple of this is always another benefit. Okay. So you have, so this is one dimension. This space is one dimension. Okay. Let us work this out in detail. What happens in R3? In R3, there are two situations. One is in R3 you have two situations. We start with a one-dimensional subspace. That is a line passing through the ball. In that case, what happens? Now there are, you see that as I said, the class of quotients form a bundle. Okay. Therefore, if you just take A, not in U, this is suppose LU. Okay. If you just take LUA, see it's a line parallel to this. Fine. And if you take scalar multiples of that, what you produce? You will cover only the space spanned by U and A. Okay. So you will be only partly covering the space. Therefore, if you fix your A and along with A and U, you have see LA, take this connection for a fixed A. Now this could be a basis, a single vector, but which will cover only lines parallel to the given line, but all lying in the same plane. So you will cover the two-dimensional part of it. But suppose you want to cover the entire space, then you also need such that A and B not that means B is not a scalar multiple of. So if you choose a B which is not a scalar multiple of A, then you get other vectors. And in fact, if you take the linear combination of A and B in that case, and then construct the quotients using that, you can get all the lines parallel to A. Now this is the scenario that you have. So choose two vectors linearly independent, and then you use LU, L, U, A, L. These lines are not the same. Every line LUC parallel to LU can be written as a linear combination of the two lines LUA and LUB, which are parallel to LU. In fact, A and B have to be linearly independent. LUC can be written as lambda times L mu times L. This is what you can do. Why it is so? Because lambda times LUA plus mu times LUB is equal to LU and choose such that if A and B are linearly independent, and then you can choose a C such that this is equal to lambda A plus U. Okay? And what do you get? Then you see that L now this is a vector. See, you choose a vector C that lies in the plane spanned by A and B. Then you see that this is equal to L U, right? Therefore, every vector can be generated or every line can be generated in the form lambda a plus mu b, where a and b are not taken along the line and u, and such that a and b are linearly independent. Such a choice is possible because we are now having such a choice is possible because you are in the three-dimensional space and one dimension is taken care of by you. The other two vectors you can choose. In whichever way you want, you can choose such that they are linearly independent. If you generate that, then you have L UA and L UB, and the collection L UA for fixed A and B, as we have chosen, will serve as a basis for the Quotient collection of lines parallel to the given line. So it is essentially a two-dimensional space that you end up with. Here you end up with a one-dimensional space. At the same time, suppose you were to work with R3, in which you start with a two-dimensional subspace. Then you see this is generated by, this is the span of U and V. Take the span of these two. This is it. Now there exists a vector A belonging to R3 such that A does not belong to, because it is three-dimensional, you have a third vector. Or in other words, U, V, A together will form what is called a basis for R3. Now you look at this class, L, A. This would form a for the vector space of all planes parallel to so essentially this is the collection of all LUV is now a one-dimensional space. Okay, so we have now several kinds of scenarios that we have worked out. Now we will try to work out, these are called quotient spaces. So actually the whole space is given, then you are quotienting with the subspace that you choose. In R3 you have got R3 by R2, you have R2 divided by, you write like this. The subspace generated by you. Then in R3 you have two scenarios. See, this is a line through the origin, this is a line through the origin, this is a plane through the origin. And the quotient space here is one dimensional. The quotient space here is two dimensional. And the quotient space here is again one dimensional. Therefore, in short, we can speculate that this dimension of the space minus dimension of the subspace equal to dimension of quotient space. This is a formula that apparently checks well in all these situations. Okay. So this is the analysis of R2 and R3 for quotient spaces. Now these spaces are called, the space of lines and planes that we have devised are called the quotient spaces. They are the manifestations of quotient spaces. Okay. One more observation that you make is that if you are in R2 and you start with a one-dimensional subspace, what about the complementary subspace to that? It is a one-dimensional subspace. Therefore, you see that the quotient space and a complementary subspace. In fact, there are many complementary subspaces that you can get. I'll just make it clear with a picture. See, you have in R2, suppose you have, this is your subspace generated by LU. Now you see that you can have several subspaces which are complementary subspaces. Any one of the lines passing through the origin which does not coincide with LU will serve as a complementary subspace. They all have dimension. Okay. So in short, your quotient space condenses out all these possible complementary subspaces. These are called complementary subspaces. And they are all of the dimension 1. And in fact, the quotient space also has dimension 1. So in short, we observe that the quotient space is something which is isomorphic probably to any one of these complementary subspaces. That is the answer. You can check the same thing happening in R2. In R2, suppose you start with a line, then what about the complementary subspace? The complementary subspace has a basis consisting of two linearly independent vectors. In fact, there are so you take in R3, you start with a one-dimensional subspace which is a line passing through the origin. Any plane passing through the origin and not containing this line is a complementary subspace. So there are several complementary subspaces of dimension 2. All these complementary subspaces have dimension 2. And there, in that case, you see that the quotient space also has dimension 2. So in short, here also the quotient space is isomorphic to the quotient space is isomorphic to any one of these complementary subspaces. So in short, that crucial property of the geometric structure is inherited by the quotient space of all the complementary spaces. Third case is when you start with a two-dimensional subspace in R3, you get parallel planes. Okay? They are generated by a single line. A line that cuts every one of them passing through the orbit. Okay? And that is one dimensional. Therefore, the quotient space has dimension 1. Right? Now you see that the complementary subspaces of R3, in R3 of the given two-dimensional vector space is of dimension 1 because the given subspace is of dimension 2. Okay? Therefore, again the isomorphism works. We shall in fact abstractly explore this in lessons. And that will be the theme of my next lecture. So I hope the geometry has given you sufficient insight into what are called complementary or what are called quotient spaces. Now we can formally introduce the concept of quotient space and then explore that what are the dimensions and so on and prove the isomorphism. So this will be my talk on this topic, the next talk on this topic. Okay, thank you very much.